Imagine the brightest objects in the universe. No, not the stars. Not galaxies. Blazars. These cosmic monsters shine so brightly that a single dot can outshine 1,000,000,000,000 stars combined. And you know what's the craziest? We look straight into the muzzle of the space cannon. To begin with, a blazar is not just a bright thing in the sky. This is the active core of the galaxy, where a supermassive black hole devours matter and shoots jets of energy directly at us. Literally. If this beam had missed even a few degrees, we would not have noticed the blazars at all. They would have seen an ordinary galaxy, maybe a little brighter than average. But we're lucky or unlucky, it depends on the point of view, and we're in a straight line of fire. To understand the scale, let's imagine a black hole at the center of a blazar. Usually, a black hole with a mass of billions of suns sits there. Billions. If our sun were a grain of sand, such a black hole would be the size of Mount Everest, made entirely of grains of sand suns. It's not just a big black hole. This is something absolutely monstrous in size. An accretion disk is spinning around this black hole, a giant maelstrom of gas, dust, torn stars, and anything else that hasn't escaped. The material in this disk is moving at close to the speed of light. Friction heats it up to millions of degrees. For comparison, the surface of the sun is only about 6,000 degrees. And here are millions. The disk glows so brightly that it can be seen across half of the universe. But the most interesting thing happens near the poles of the black hole. There, the magnetic fields swirled by the rotation of the disk and the black hole itself work like a giant particle accelerator. They take some of the matter from the disk and accelerate it to a speed that differs from the speed of light by literally a fraction of a percent. This matter is shot out in the form of two opposite jets.
Imagine a fountain.
An ordinary city fountain with water. Now imagine that water is a red-hot plasma flying at almost the speed of light, and the fountain itself is the size of our entire solar system. No, wait, let's do more. These jets stretch for hundreds of thousands of light years. If our solar system were the size of a golf ball, then the jet would be the size of the distance from Moscow to Vladivostok. And this whole structure is moving, pulsating, changing. When one of these jets is pointed directly at Earth, we see a blazar. It's like looking along the barrel of a galaxy-long lightsaber. The flux of radiation is so intense that the blazar can change its brightness thousands of times in a matter of hours. Imagine if the sun suddenly became 1,000 times brighter between breakfast and lunch. This is how blazars behave. Where does this energy come from? It's incredible, isn't it? A black hole, by definition, doesn't let anything out. How can it power the brightest objects in the universe? The trick is that the energy doesn't come from the black hole itself, but from matter that hasn't yet fallen inside. When gas and dust fall into a black hole, they pass through the accretion disk. There, gravity compresses them, friction heats them up, magnetic fields twist. Part of the matter eventually falls inside, but the other part, from 5 to 30%, is thrown out in the form of jets. It's an incredibly efficient process. Compared to thermonuclear reactions in stars, which convert about 1% of their mass into energy, black holes are dozens of times more efficient. They literally squeeze everything they can out of matter before it disappears behind the event horizon. Now let's talk about what exactly we see when we look at a blazar. It's not just light like from a light bulb. This is the entire spectrum of electromagnetic radiation at the same time. Radio waves, infrared radiation, visible light, ultraviolet light, X-rays, gamma rays all at once. Blazar glows at all possible wavelengths. Moreover, gamma radiation from blazars is so powerful that one photon carries an energy equivalent to the energy of a tennis ball flying at a speed of 100 kilometers per hour. This is for a single photon, a particle of light. An ordinary photon of visible light carries negligible energy. And these gamma photons from blazars are like bullets at the level of quanta. And here's the funny thing. We don't see most of the blazar's energy with our eyes at all. In visible light, they are bright, yes. But the main power is hidden in the radio range and in the gamma range. If we had eyes that saw gamma rays, the sky would look completely different. Blazars would shine like spotlights, eclipsing everything else. Scientists classify blazars into several types. There are BL lizards, named after the constellation where the first such object was found. They have almost no emission lines in the spectrum. That is, we do not see obvious traces of specific chemical elements. There are flat-spectral quasars. Their spectrum is more diverse, emission lines are visible. But in fact, they are still the same animal, just from different angles and in different states. By the way, about quasars. Blazars are a subtype of quasars. A quasar is a quasi-stellar radio source, an object that looks like a star but shines like an entire galaxy. When astronomers first saw these things in the 1960s, they didn't know what they were. The object looks like a dot, like a star, but the spectrum is completely insane and the brightness is beyond limits. It took time to realize. These are not stars. These are the cores of distant galaxies, where black holes devour matter. And blazars are those quasars whose jets are pointed directly at us. Roughly speaking, if we look at the active nucleus of a galaxy from the side, we will see a quasar or radio galaxy. If you look along the jet, there is a blazar. It's a matter of geometry and luck. How far away are the blazars? Very far away. Most of the known blazars are located billions of light years away. The light from them flew towards us for most of the age of the universe. When we look at the blazar, we see it as it was when the universe was several times younger. Maybe that blazar no longer even exists in the form in which we observe it. Maybe the black hole has already eaten up all the gas nearby and gone quiet. But the light is still flying towards us, and we see an ancient show. The most powerful blazars are so far away that their light has been coming to us for 10, 11, 12 billion years. The universe is only about 14 billion years old. That is, we see objects that were active when the universe was less than 2 billion years old. At that time, galaxies were just forming, colliding, merging. Black holes grew rapidly, devouring huge amounts of gas. This was the heyday of quasars and blazars. There are fewer blazars now than there used to be. Or, more precisely, we see fewer active ones. Most of the black holes in the centers of galaxies are now asleep. They've eaten all the gas available and just sit there, huge and inactive. Our own black hole at the center of the Milky Way, Sagittarius A*, is just that. It's massive, about 4 million times the mass of the Sun, but it's not actively feeding. If it were to start devouring gas intensely, and if its jet were to accidentally head for any part of the galaxy, it would be a sight to behold. But so far it is quiet. Although even quiet, it sometimes flares up. In 2019, astronomers noticed that Sagittarius A** suddenly became 75 times brighter than usual. It lasted a couple of hours, then everything returned to normal. Most likely, some large object fell there, maybe an asteroid or maybe a cloud of gas. The black hole tore it apart and flared up brightly for a short time. Imagine if she did it all the time. Imagine if the jet was aimed at us. We would live in a galaxy with a blazar at the center. Fortunately, this does not happen. But let's imagine for a second, what would happen if the blazar was closer to us? Say, not billions of light years away, but only a few thousand, or hundreds. The radiation would be so intense that it could damage the Earth's atmosphere. Gamma rays destroy ozone molecules. Without the ozone layer, the surface of the planet would be under direct ultraviolet radiation from the sun. Life as we know it would be impossible. Some scientists even suggest that gamma ray bursts from distant blazars or similar objects may have influenced life on Earth in the past. There is a theory that one of the mass extinctions, the Ordovician-Silurian extinction, about 450 million years ago, may have been partly caused by a gamma ray burst from a relatively nearby cosmic object. There is little evidence, but the idea is interesting. Space can kill not only with asteroids. However, the blazars are far enough away not to pose a threat. But they give us the opportunity to study extreme physics. In blazar jets, matter moves at a speed very close to the speed of light. So close that relativistic effects begin to appear. Time slows down, lengths shorten, masses increase. And we can observe it in real time. One of the strangest effects is called superluminal motion. Sounds like a violation of the theory of relativity, right? Nothing can travel faster than light. But when a jet of matter travels at almost the speed of light and is directed almost directly at us, an illusion arises. We see how clumps of matter in a jet move faster than the speed of light. This is not true FTL motion. It is an optical illusion caused by geometry and light delay, but it looks impressive. Here's how it works. Imagine that a jet ejects a blob of plasma that flies towards us at a speed of, say, 99.5% of the speed of light. The clot flies at a slight angle to us, almost straight. The light from the clot also flies towards us, but at the speed of light. As the clump almost catches up with its own light, the difference in the arrival time of photons from different points in the trajectory is compressed. To us, it looks as if the clot has moved a long distance in a very short time. Mathematics shows that the apparent speed can be several times the speed of light. In reality, nothing moves faster than light, but the illusion is perfect. Astronomers have observed this in many blazars. The jet is filmed at intervals of several months or years, compared and seen. The clumps have shifted to distances that, if counted directly, correspond to speeds of 5, 7, even 10 speeds of light. This is one way to confirm that the jet is indeed aimed almost directly at us. Now let's talk about variability. Blazars are incredibly volatile. Their brightness can vary by orders of magnitude for days, hours, even minutes. This tells us something important about the size of the emitting region. If an object changes brightness in an hour, then the size of the source cannot be more than 1 light hour. Otherwise, different parts of the source would not be able to coordinate their radiation. The light simply would not have enough time to travel from one edge to the other. A light hour is the distance that light travels in an hour. About 1 billion kilometers, a little more than the distance from the Sun to Saturn. This is very little by cosmic standards. It turns out that a source of incredible brightness, which can outshine an entire galaxy, fits into a volume the size of the orbit of Saturn. How is this possible? Answer: relativistic amplification. When a jet travels at nearly the speed of light towards us, its radiation is amplified. The effect is called Doppler boosting. The photons are compressed, their energy increases, and we see a brightness that is tens or hundreds of times greater than it would be if the jet were standing still. It's like someone with a flashlight running towards you very fast. The flashlight seems brighter. Add to this the changes in the jet itself. Turbulence, magnetic reconnections, shock waves, and you get a chaotic, rapidly changing picture. Blazars are not stable objects. These are seething, pulsating monsters. Sometimes blazars flash especially brightly. This is called flash or flare. During a flare, the brightness can increase thousands of times in a few hours. In 2017, a blazar called TXS0506+056 produced such a powerful flare that it was spotted not only in the electromagnetic spectrum, but also in neutrinos. This was the first time that astronomers were able to link a high-energy neutrino source to a specific space object. Neutrinos are almost elusive particles. They fly through matter as if it does not exist. Billions of neutrinos from the Sun pass through your body every second, and you don't feel it. To catch neutrinos, you need huge detectors hidden deep underground or under ice. One such detector, IceCube, is located at the South Pole. It consists of thousands of sensors frozen into a cubic kilometer of Antarctic ice. In September 2017, IceCube detected high-energy neutrinos. Scientists quickly determined the direction from which it came and asked other telescopes to look there. It turned out that it was at that moment that the Blazar TXS0506+056, located at a distance of about 4 billion light-years, was experiencing a powerful flare. The coincidence was too exact to be accidental. This discovery is important because it confirms that blazars are one of the sources of high-energy cosmic rays. Cosmic rays are particles, mainly protons, that travel through space with enormous energies. Some are so energetic that a single particle carries an energy comparable to that of a thrown baseball. This is madness at the level of one subatomic particle. Where do these superenergetic particles come from? For a long time, scientists did not know. Now we understand that blazars and their jets are one of the accelerators. Magnetic fields in jets accelerate protons to incredible speeds. When a proton collides with a photon or other particle, new particles are born, including neutrinos. These neutrinos fly directly towards us, through the entire universe, without being deflected by magnetic fields, and convey information about their source. Electromagnetic waves also convey information, but they can be scattered, absorbed, and deflected. Neutrinos travel in a straight line. This makes them ideal messengers from the most extreme events in the universe. By the way, about the messengers, by studying blazars, we can look into the past of the universe. Blazars were more common billions of years ago, when galaxies were actively forming and colliding. Galaxy collisions are catastrophic events. Two galaxies are approaching, their gravitational fields interacting, stars, gas, and dust are mixed. The black holes at the centers of galaxies also get closer together and can eventually merge into one even more massive black hole. During the collision, a huge amount of gas falls towards the center of the combined system. The black hole begins to feast. The accretion disk heats up. The jets intensify. A galaxy for a short time, short by cosmic standards, maybe a few million years, turns into a quasar or blazar. Then the gas runs out. The black hole eats up everything that was nearby. The jets fall silent. The galaxy is becoming quiet. The black hole remains, huge and dormant, in the center. This is the fate of most galaxies with massive black holes. Our Milky Way may have once been a quasar, too, billions of years ago when it was young and full of gas. By the way, about the future, in about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. This clash will be grandiose. The two largest galaxies in our local group will merge into one elliptical galaxy, which astronomers have already nicknamed Milkomeda or Milkomeda. During the collision, the gas will rush to the center. Our black holes, Sagittarius A* from the Milky Way and the more massive black hole from Andromeda, will eventually meet and merge. Perhaps for some time the united galaxy will become a quasar, or maybe a blazar, if the jet accidentally heads towards some star system. If humanity still exists in one form or another, we will have a spectacle right on our doorstep. Although at the doorstep is a big word. The center of the galaxy is 26,000 light-years away. Even if a blazar flares up there, we will be relatively safe. Relative. But let's get back to the present. How do astronomers study blazars? Mainly through telescopes observing in different ranges. Radio telescopes, such as the Very Large Array in New Mexico or ALMA in Chile, see radio emission from jets. Optical telescopes like Hubble observe visible light. X-ray telescopes like Chandra or XMM Newton catch high-energy photons. Gamma-ray telescopes, such as Fermi or ground-based Cherenkov telescopes, detect the most energetic radiation. By bringing the data from all these instruments together, astronomers can build a complete picture of what's happening in the blazar. This is called multi-wave astronomy. Each range gives its own piece of the puzzle. The radio shows the structure of the jet. Optics and ultraviolet light are a disk. X-rays are hot plasma around a black hole. Gamma rays are accelerated particles. One of the interesting questions astronomers ask is, how exactly do particles in jets accelerate? We know that magnetic fields play a role, but the details are unclear. There are several models. One of them is shock waves. When fast matter in a jet crashes into slower matter, a shock wave is formed that can accelerate particles. Another model is magnetic reconnection. The magnetic fields in the jet can twist, break, and reconnect, releasing energy and accelerating the particles. Most likely, both mechanisms work depending on the conditions. Jets are chaotic, turbulent flows. There's a lot going on there at the same time. Another mystery: how are the jets themselves formed? We know that they are related to the rotation of the black hole and the magnetic fields of the disk, but the exact mechanism is still debated. The most popular model is the Blandford's-Notchka mechanism. According to this theory, a spinning black hole can transfer its rotational energy to the magnetic fields around it. These fields, twisted by rotation, carry energy and matter out in the form of jets. It's like a skater who spins and then stretches his arms. The energy of rotation passes into the hands, and they fly apart. Only here, instead of hands, there are plasma jets flying at a speed close to the speed of light, at distances exceeding the size of galaxies. There is an alternative model, the Blandford-Payne mechanism, where energy is taken not from a black hole, but from a disk. The magnetic fields in the disk are twisted by its rotation and push matter outward. Both models may work at the same time. The black hole gives the main power and the disk adds its own. Recent observations with the Event Horizon Telescope, a network of radio telescopes scattered around the world that work together as one huge telescope the size of Earth, have made it possible to see the surroundings of black holes with unprecedented resolution. In 2019, the EHT presented the first image of the shadow of a black hole in the galaxy M87. This is not a blazar but a radio galaxy, but the principle is the same. A supermassive black hole and accretion disk jets. The image shows a glowing ring. These are photons that almost fell into the black hole, but still managed to fly away. In the center is a shadow, an area from which light cannot escape. The size of the shadow corresponds to the event horizon of the black hole, magnified by lensing. And you can see the asymmetry in the ring. One side is brighter than the other. This is the Doppler effect. The matter on one side of the disk is moving towards us, and its radiation is amplified. For blazars, such observations are even more difficult because we are looking directly into the jet. Jet is so bright that it outshines everything else. But astronomers are working on it. Perhaps in the coming years we will see detailed images of blazar jets taken by the EHT. Interestingly, blazars also help us test fundamental physics. For example, the speed of light. According to the theory of relativity, the speed of light in a vacuum is the same for all frequencies. But some theories of quantum gravity suggest that at very high energies there may be tiny violations of this principle. Photons with different energies could move at slightly different speeds. If this is the case, then the photons coming out of the blazar at the same time will arrive at different times if they have different energies. The difference would be microscopic, but for objects billions of light years away, the effect could accumulate. Astronomers observed blazar bursts, where high-energy and low-energy photons arrived simultaneously to within milliseconds. This places strict limits on possible violations of the principle of the constancy of the speed of light. So far, no violations have been found. Einstein was right again. Blazars also help study the intergalactic environment. Light from a distant blazar travels great distances, crossing clouds of gas, galaxies, and clusters of galaxies. Some of the light is absorbed along the way. By analyzing the spectrum of a blazar, astronomers can see absorption lines and determine which elements are present in what quantities along the way. This provides information about the chemical composition of the universe, how the gas is distributed among galaxies, and how it has evolved over time. Blazars, in fact, serve as beacons that illuminate the structure of the universe. There is another intriguing aspect. Blazars can influence the evolution of their galaxies. Jets carry a huge amount of energy. When a jet slams into interstellar gas inside a galaxy, it heats it up, sometimes to the point where the gas can no longer cool and collapse to form new stars. This is called feedback from the active galactic nucleus. A black hole, while devouring matter, simultaneously restricts its own nutrition because it blows out gas that could fall into it. And at the same time, it suppresses star formation in the galaxy. This may explain why there is so little star formation in the most massive galaxies. They are full of old stars, but almost no new ones are born. It's likely that their central black holes were so active in the past that they blew out all the gas or heated it too much. Blazars are an extreme case of this process. Their jets are so powerful that they can clear the entire galaxy of gas, or at least a significant part of it. This sounds devastating, but it may actually be necessary for the evolution of galaxies. Without feedback from black holes, star formation would take too long. Gas would fall into the center of the galaxy, form stars, and eventually the galaxy would become too dense, too massive. But black holes intervene and say, "Enough!" They set the balance. This is one reason why studying blazars and other active nuclei is important, not only for understanding black holes, but also for understanding galaxies in general. Black holes and galaxies evolve together. They influence each other. By the way, an interesting fact, the mass of the central black hole is usually about 1/1000th the mass of the bulge of the galaxy, the central thickening where old stars are concentrated. This ratio is fairly stable for most galaxies. Why is that? Probably it is because of the feedback. The black hole grows until it becomes powerful enough to stop further gas flow. Then both it and the galaxy stop actively growing. Blazars represent a stage when a black hole is still growing, still devouring gas. Later, they will calm down, become ordinary galaxies with dormant black holes. Let's now talk about some specific blazars that are particularly interesting. One of the most famous is the 3C273. It was one of the first quasars discovered in the early 1960s. It is so bright that it can be seen in a small amateur telescope, although it is more than 2 billion light-years away. For comparison, the Andromeda Galaxy, the closest large galaxy to us, is only 2.5 million light-years away, 1,000 times closer. And to see Andromeda, you need dark skies and good eyesight. And 3C273 is visible through a telescope, being 1,000 times farther away. That's how bright he is. 3C273 has an optical jet, a jet coming out of the nucleus. The jet stretches for hundreds of thousands of light-years. It has clumps that seem to move faster than light. This is exactly the superluminal effect that we have been talking about. Another famous blazar is Markarian 421, MRK 421. It is one of the nearest blazars, only 300 million light-years away. Total, again, by cosmic standards. This makes it an ideal target for detailed observations. MRK 421 is very volatile. Its brightness can change tenfold per day. Astronomers observe it constantly, trying to catch the moment of the flare and understand what causes it. There is also BL Lacerti, the object that gave the name to an entire class of blazars. It is about 1 billion light-years away. For a long time, it was generally considered a variable star in our galaxy. It wasn't until later, when technology improved, that astronomers realized that this was the distant core of a galaxy. The farthest blazars are at redshifts greater than 5. Redshift is a measure of how much the light of an object has stretched during its journey due to the expansion of the universe. A redshift of 5 means that the universe has expanded 6-fold since the light left the object. This corresponds to a distance of more than 12 billion light-years. At these distances, we see the universe as it was when it was less than 1 billion years old. Galaxies were just beginning to form, but black holes were already huge, billions of times the mass of the Sun. How did they manage to grow so fast? This is one of the mysteries of modern astrophysics. Perhaps the first black holes formed from very massive stars that collapsed directly, without a supernova explosion, or from dense star clusters, where black holes quickly merged with each other, or from the direct collapse of gas clouds in the early universe. There is no answer yet, but blazars are helping to study this problem. Another interesting phenomenon is the change of type. Some blazars sometimes change their spectral class. An object that was a BL-lac type suddenly begins to show emission lines and becomes similar to a quasar, or vice versa. This suggests that classification is not a rigid separation, but rather a spectrum of states. A blazar can change from one state to another depending on how much gas falls into the black hole, how the disk is organized, and at what angle we see it. By the way, about the corners. Blazar jets are not absolutely straight. They can bend slightly, precess like a spinning top. The axis of rotation of a black hole may not coincide with the axis of rotation of the disk, especially if the black hole has recently swallowed another black hole or if mass has fallen on it from an unusual direction. In this case, the jet can change direction over time. If the jet was initially pointed at us and we saw a blazar, and then the angle changed by at least a few degrees, the brightness would drop dramatically. We will stop seeing a blazar and see an ordinary quasar or radio galaxy. The opposite is also possible. A quiet radio galaxy suddenly becomes a blazar if the jet turns towards us. True, such changes occur slowly, on the scale of thousands or millions of years. We won't see it in real time, but by observing many objects in different states, we can assemble a picture. Now, a little about the technical side of observations. How do blazars find them in the first place? There are so many of them that it is impossible to check every point in the sky. Usually, astronomers use sky surveys, automatic programs that photograph the sky as a whole or large pieces of it in different ranges. Then computer algorithms analyze the images, look for objects that look unusual. Blazars stand out for their brightness and variability. An ordinary star shines steadily. An ordinary galaxy too. But if the object flashes, changes brightness, and even shines very brightly in the radio or gamma range, this is a candidate for blazars. Then astronomers take the spectrum of the object. Spectrum is the decomposition of light into its component frequencies. From the spectrum, you can determine the redshift, which means the distance. You can see what elements are present, how they move. If the spectrum shows wide emission lines and characteristic signs of an active galactic nucleus, plus variability is visible, plus brightness in different ranges is suitable, bingo is a blazar. Modern surveys such as the Sloan Digital Sky Survey or panoramic telescopes such as the ZTF or LSST, Legacy Survey of Space and Time, which is just getting started, find thousands of new blazars every year. The LSST especially promises revolution. This telescope will photograph the entire southern sky every few nights for 10 years. It will catch every variable star, every transient, every blazar in its field of view. There will be so much data that astronomers are already preparing for an information deluge. You'll need powerful computers and machine learning algorithms to handle it all. But the results will be amazing. We learn much more about the variability of blazars, about rare events, about correlations between different types of objects. By the way, about machine learning. Artificial intelligence is already being used in astronomy to classify objects. Neural networks are trained using examples. This is a blazar, this is a quasar, this is an ordinary galaxy. The network can then classify new objects on its own, often better and faster than a human. This is especially useful when you need to process millions of objects. But machine learning is not a substitute for astronomers. It helps them focus on the most interesting objects. The computer weeds out the banal, leaves the unusual, and people study the unusual. Let's get back to physics. One of the interesting things that blazars allow us to study is intergalactic background radiation. The universe is filled with a faint glow left over from stars and galaxies that have existed throughout history. This radiation covers the entire spectrum, from radio waves to gamma rays. Gamma rays from distant blazars collide with photons of this background radiation on their way to us. A high-energy gamma-ray photon and a low-energy background photon can interact and produce an electron-positron pair. This reduces the number of gamma photons reaching us. The extent of this attenuation depends on how much background radiation is on the way. By measuring how the spectrum of a blazar changes at different distances, astronomers can estimate the density of intergalactic background radiation. This helps to understand how many stars have been born in the universe throughout its history, how galaxies have evolved. It's a tricky technique, but it works. Blazars once again serve as a tool for studying the universe as a whole. Now let's talk about the future of research. What questions do astronomers hope to solve in the coming years? First, the detailed structure of the jets. We know that jets exist, we see them on a large scale. But what happens at the base of the jet, right next to the black hole? The Event Horizon Telescope is working on this. With its help, it will be possible to see exactly how the jet starts, how it accelerates, and how magnetic fields are organized. Secondly, the connection of blazars with other high-energy phenomena. We know that they emit neutrinos and gravitational waves. When two black holes merge, they emit gravitational waves. If one of the black holes is active, can this somehow show up in the electromagnetic spectrum? If a blazar suddenly flares up, is it worth looking for a match with a gravitational wave event? So far, no such coincidences have been found, but gravitational wave detectors are becoming more sensitive. LIGO, Virgo, CAGRA, and in the future, the space detector LISA. We may soon see the first combined event. Gravitational waves from a black hole merger, plus an electromagnetic flare from a blazar. Third, the role of blazars in the early universe. New telescopes like the James Webb Space Telescope are already finding galaxies at redshifts greater than 10, that is, when the universe was less than 500 million years old. Are there blazars among them? If so, it says that black holes grew incredibly fast. This is changing our understanding of the formation of the first galaxies. And finally, the practical aspect. Blazars can be used as standards for cosmology. Their brightness and spectrum provide information about distance. If you learn how to calibrate them correctly, blazars can become another tool for measuring the expansion of the universe, determining cosmological parameters, and testing the theory of gravity on large scales. The universe is vast, and blazars are some of the most notable beacons in this vastness. They are not just bright dots. They are windows into extreme physics, into the history of space, into processes that cannot be reproduced on Earth. When you look at a blazar, you're looking at a black hole that weighs billions of suns, a disk of incandescent matter moving at nearly the speed of light, jets of plasma stretching across the galaxy. You're looking at an object that can outshine 1 trillion stars. And you look at all of this from billions of light years away, you see an event that happened when the universe was several times younger. This is not a fantasy. This is reality. Blazars exist. They are there, in the depths of space, doing their job. Devouring matter, emitting energy, forming galaxies, sending neutrinos and cosmic rays in all directions. And we, tiny beings on a small planet, can observe it, study it, understand it. Science gives us superpower, the ability to see the invisible, to understand the incomprehensible. Blazars are one of the greatest wonders of the universe, and we're just beginning to uncover their secrets. In the coming years and decades, we will learn even more. New telescopes, new detectors, new methods of analysis. Each observation brings us closer to a full understanding of how these space monsters work. And who knows, maybe someday we'll even find a way to harness the energy of black holes. Sounds like science fiction, but once upon a time, space flights seemed like science fiction. A civilization capable of extracting energy from the accretion disk of a black hole would be incredibly powerful. Such a civilization would be a Type 2 or even 3 on the Kardashev scale, controlling the energy of a star or even a galaxy. We are still a Type 0, not even fully controlling the energy of our planet. But we are learning. We look at blazars, we look at quasars, we look at other wonders of the cosmos, and we learn. We study physics, learn engineering, learn to dream. Blazars remind us how big and strange the universe is, how small we are and how much remains to be discovered. It's both humble and inspiring. We may feel like grains of sand in the face of the cosmos, but we are thinking grains of sand. We ask questions. We are looking for answers, and sometimes we find them. So the next time you hear about a blazar, remember, it's not just a bright in the sky. It's a star-devouring black hole. These are jets firing through the galaxy. It's a window into processes where matter and energy behave like nowhere else. It's part of the great history of the universe, a story we're just beginning to read.